So by considering various types of systems, we saw that minimums in the Helmholtz or the Gibbs energy can serve as indicators that a system is at equilibrium. Okay? Alright, so if A reaches its lowest value or G reaches its lowest value for a system, that would indicate that that system is at equilibrium. Okay? But there's a bit of a complication here, because in general, our Helmholtz energy or the Gibbs energy of a system, they're not going to be very simple functions. A lot of times, they're very complex functions of other properties, if you will, or other parameters. So for example, pressure, volume, and temperature. Okay? And so, if we looked at the Gibbs energy as a function of pressure, we may not just see that the Gibbs energy has a single minimum in its value. We may see that there's many different pressures that minimize the Gibbs energy. Okay? And so in order to sort of overcome these complexities, or at least be on the same page about these complexities, we need to define some terminology so that we can be more precise in our conversations and discussions about equilibrium. Okay? So we must define some terminology. Okay? Alright, so I'm going to define a couple of different terms that are used to describe how equilibrated a system is. Okay? Alright, so the first term I'm going to define is stable. Alright? And so when I say stable, or when I say a system is stable, I mean that if some property X of a system is perturbed from its initial state, the system will eventually revert back to its original X value. Okay? Alright, so that's what I mean by stable. It's a bit of an abstract definition. And so to make this a little bit more clear, I'm going to draw an illustration for you. Okay? And so on these axes, the y-axis is going to be either your Helmholtz or your Gibbs energy. It doesn't matter which one. And the x-axis here, we're going to say this is just some property x. Could be pressure, could be volume, could be temperature, could be whatever. Right? It's just some physical property of the system. Right? Now, when we say a system is at equilibrium or it's stable, imagine that, we trace out the Helmholtz or the Gibbs energy of the system as a function of x. And we see, in this case, it forms a parabola. And the minimum of this parabola is right here. Okay? And so, let's say our system had an x value such that its Gibbs energy was right at that minimum. Okay? In fact, when we say that the system is at that state, you can imagine that the system is like a little ball here. Okay? Alright, and so let's say the system is initially has a value of x such that the Gibbs energy is at that minimum. Okay? And then let's say you do something to the system to quickly change x or perturb it. Right? So if you had a piston cylinder system, imagine that initially the system was stable, and then you quickly applied a force on the piston to compress it. Right? And so by doing that, what you would do is you would move the system to a higher free energy state. Okay, so its free energy would increase away from the minimum, right? So you applied a force on this gas and you raised its free energy. But then let's say after you quickly apply that force, you then let go, right? And you remove that force. Okay? And so now that that force is gone, the system, is going to want to move towards a more equilibrated state. And so it will then begin to decrease its pressure again until it's back to the bottom of that parabola, till it's back to that lowest Gibbs energy state, right? And so when I say the system is perturbed, you do something to move this little ball left or right, but then once you remove that force, or that driving force, and then let the system, act like it was before, the system, that ball, will just go back to the minimum. Okay? If we have a system like that, or if we have a situation like that, we would say that the system is stable, right? It's always going to return back to its original equilibrium state. Okay, so that's what we mean by stable. The next term I want to define is metastable. Okay. All right, and so if we have a metastable system, what that means is that the system has other states with lower energy than its initial state. Okay? And if the system is perturbed, it returns to its original position if those changes in property X are just very small. Small compared to some what we call energy barrier. Okay? But on the other hand, if the changes in X are large, larger than that barrier, the system may go to another state. Okay. All right, so that's, the definition of metastable in words, but let's illustrate it using the same sort of plot that we used previously. Okay? So the y-axis is still A or G, x-axis is still property X. And so if we have a metastable system, we wouldn't expect a curve like this, but rather we would expect a curve like this. Okay? And let's say that the initial state of our system is here. Right? And we see that in the state of the system, it's at a minimum in its energy, in its Helmholtz or its Gibbs energy. But it's not like a global minimum, right? In fact, what we have here is like a local minimum. And we see if we trace along other parts of the curve that there's also other minimums in the energy, like one here. Okay? But in any case, initially the system is in some sort of equilibrium state. here. But then let's say we perturb the system somehow to change x. Okay? And so if the perturbations are small, if we change x only a little bit, the system will go up here, but it will eventually just return back to its initial state. But if we change x a lot and perturb it a lot, this ball here would then get knocked into a completely new state here. Right? And then it wouldn't return back to its original state, but rather it would get stuck in a valley that we see over here in a new equilibrium state. Okay? So that's what we mean by metastable, is that the system, it's initially stuck in some sort of low energy state, but if you perturb pressure, volume, or temperature enough, then you may cause the system to change irreversibly into another state. And you could see here, in order for it to go to that new state, this ball here has to like go over this hill or this barrier, right? And so that's what we mean by an energy barrier. It's literally the system has to gain enough energy at some point in order to then end up at this lower energy state here. And so we quantify the size of that hill by calling it an energy barrier, or an EB. Okay, so that's what metastable means. It means that your system, if you perturb it enough, you may cause the system to reach a completely new equilibrium state. Right. The next term, I talked about stable and metastable there. But now what I want to talk about is unstable. Okay? And so if you have an unstable system, what that means is that if you have any changes in x, no matter how small, those changes will take the system to another equilibrium state. And so an unstable system, its energy diagram would look like this, where imagine you have a hill like that, and then initially your system starts on top of this hill, right? And so any movement from, if you increase x or you decrease x, are just going to knock it off the top of the hill into a completely different state instead, right? So that's what we mean by unstable. And then the last term I want to define is something that's neutrally stable. And if something is neutrally stable, essentially what that means is that your property x doesn't affect A or G. Okay? And so here, what you would see in your energy diagram is that if you change x any direction, A or G would just be the same. And so an example of this would be if you have a truly incompressible solid, if you change the pressure of your system, because that solid's incompressible, you're not going to affect its free energy at all, right? And so that would be a case where a system is neutrally stable towards pressure. Okay? All right, and so we define these terms. We define stable, metastable, unstable, and neutrally stable. And so we're going to use these terms in order to describe, the equilibrium and stability of various chemical systems.